your homework, I put up your Chapter 6. The rest of your My Math Lab homework is up. 6.4, mostly what you're going to do on this is you're going to do graphs with your calculator. So it's just mostly you want to know how to do that. You will see this kind of stuff in Calc 2. Like this morning when I was teaching my Calc 2 class, we were going over kind of reviewing how you do some of these things, and mostly we're doing a calculator, and we started working with polar coordinates quite a bit in Calc 2 at the end of the semester. So this one, what you want to do, just to kind of get an idea, you'll see this stuff again, is you would want to take the square root of both sides. If you're going to put this in your calculator, you got to do this like this. You'd have to take square root of both sides, and when you do that, you're going to have a plus or minus. So we'd just do 36 sine of 2 theta like that, and then you would have r is equal to that. Now one thing you could do is the square root of 36 is 6, and then you would still have the sine of 2 theta under a radical. You don't need to do anything with that since we're doing that on the calculator. We don't need to simplify it or anything. So let's see what I'll have you do on this. So basically what I'll have you do is we'll just put the plus part in here. The minus part isn't really going to make any difference on this, so we're going to put in 6 and then square root, whoops, dang it, 6 and then square root of sine of 2 theta. Okay, now let's see, for a window, you always got to think about how your window goes on this. The 6 is the key. That means this is going to be, this curve is going to go out 6 units on this. So what we're going to do on this is do your theta step like this, 0 to 2 pi. Make sure you're in Radian mode like we were in Tuesday night's class. Theta step small, 0.1. And then x and y, just make those like -7 to 7. I'm going to take it out that far and by a scale of 1, and then we'll see what we got. Okay, this is called a lemniscate. And you guys are not required to know the names of these. You're not ever going to be tested over the names of these things. But it's just kind of good to have a background for it because you'll see it again if you're going to go into Calc 2 is when you see this again. Now, all I'm having you guys do on this is just sort of sketch this. You can actually, in polar coordinates, you can trace. So if you want to get a few points, you can. You can go like this. You can trace 0. And if you trace at 0, oops, that didn't work. Let's try that again. Trace at 0. I'm not sure why. Yeah, okay, you have a point 0, 0. And you can just sort of estimate this. So you have that. And when you have a point 0, 0, you can think of that as being an XY point like that. And then you can just kind of press your cursor key and just kind of estimate a few points. Like this point is about, it's almost like 5, 3 or something like that. So just estimate, go over 1, 2, 3, 4, 5. And just all I want you to do is just sort of estimate these points like that, and then just sketch in the curve like that. Same thing happens here. I think if you continued to trace through that, what's happened is the angle is getting bigger and bigger and bigger, and then you start kind of moving over in here a little bit. Where's my cursor? There it is. Okay, so you kind of get over in here, so that's roughly around 1, 2, 3, 4, and down about 3 like that. So just sort of guesstimate it like that, and that's good enough for what we're learning anyway. So that's called a lemniscate, okay? All right, and what happens is it kind of goes diagonally because that's a sine, all right? Let's do the next one also. Just do this the same way. You should be able to just kind of slightly change this to square root of both sides. You'll have r equals plus or minus 5 times cosine of 2 theta like that. Okay, so you can type over that or clear it out and put this new thing in. So I've got 5, and then I've got square root of cosine of 2 theta. Okay, we can probably use the same viewing window, should be sufficient on this problem. This will look kind of like an infinity, and it'll go around the x-axis like this. And this one's a little easier to graph. You go 1, 2, 3, 4, 5. That's the meaning of that square root of 25. So on the x-axis, you go out 1, 2, 3, 4, 5 circles. On the y-axis, the same thing. And then you kind of trace through this like this. One thing that kind of helps you learn about polar coordinates graphs is if you trace and start by tracing at 0, that shows you that this graph actually starts there. Okay, it actually starts at the 0.00. Then if you press your right cursor key, it'll kind of show you how this traces through this figure. Okay, and it'll kind of take it a while to get back on here, but I just keep tracing through that, and then it'll show you how, as those angles get bigger, that's how it runs through that. So this one kind of starts here, then it goes like this, kind of jumps up there, then it kind of goes in kind of like that. Okay, that's also a lemniscate. Okay, and what lemniscates tend to look like is they're usually r squared equals a squared, and it's either cosine of 2 theta or it's sine of 2 theta like that. Okay, that's the structure. You don't have to know those formulas. That's not necessary. Just kind of good to get some of these things just so you're familiar with them for the future. Okay, is everybody's calculator working okay? Because that's mainly what we're going to spend our time on polar graphs is calculator stuff. Okay, when you do get into that test 3, any polar graph I have you do, you'll be able to use your calculator on. Yes?
Whenever I try to trace, it doesn't actually trace the object.
What's that?
Whenever I trace, it's not tracing the object.
Okay, you're not getting anything on that?
No.
It could be, which calculator do you have?
83 plus.
Okay, that's a little older calculator. So you're just typing trace. Did you put a number in like 0? Just type trace and then put a number in like 0 to start with. And then see if a cursor comes up on 50. Is anything coming up?
Oh, yeah.
Okay. Now if you just press your right cursor key, it should trace through there. And it depends on which model of calculator you have. I usually just put in an initial point of 0 and then trace to kind of see the order it goes through the curve. Okay. All right. Anybody else have any trouble with the calculator? Okay. All right. Okay. Let's go to the next page then. Did I show you guys the cannabis curve?
Yes.
Okay. Did anybody take the time to put it in? I didn't think so. Okay, but you can. No extra credit for that, but you could if you want to. All right, let's look at this one and put this in your calculator. All right. So let's see. I'm going to clear this off. So we've got 4 sine 5 theta. This is what's called a rose curve. It should have 5 petals because of the 5 theta. Okay, and each petal I think will go out 4 units on the radius of 4, if I'm remembering right. So it just kind of goes like that, okay? Probably that cannabis curve is really sort of a derivative of a rose curve that somebody has just really worked with to try to get down a little bit more interesting looking, okay? So this one basically goes like this. All I want you to just kind of trace out on here is the 4 is telling you that that's going up 1, 2, 3, 4 there. And then you'll have kind of a curve that goes through like this. And then the rest of it just sort of estimate. This thing's supposed to go out 1, 2, 3, 4, kind of in there and so forth. So just kind of do the best you can to estimate that through that pole. Go like that. That's pretty sloppy on my part, but you get the hang of it. Mainly like for a test, I'm probably a little bit more interested that you can do a cardioid and that kind of thing because that's the #1 thing. Yeah. What's that? Oh, you got that? That's really cool looking. Let's check 2 things. Let's check your mode. You're in Radian mode. Okay, your plot's on, and I'm going to turn that off, and your step could be a little weird too. So if you go to your window, that's what I thought. When you have a step of 1, it makes it look real rigid. It's not like a nice smooth curve. So I'll put a 0.1 in there, and there you go. Okay?
Thank you.
All right. Okay. Everybody got that okay? Okay, so that's called a rose curve. And the basic structure on this is if you have like a sine, it's like this. The equation is r equals a sine b theta. Okay, that will tell you the number of petals that you have. So if you experiment and put like, I'll just do this one more time. Let's change the 5 maybe to 9, and let's see if we don't indeed have 9 petals. Okay, look at that. Okay, and so forth. So it goes like that. It's different on a cosine. The next one, let me show you a cosine. I don't have that on my notes, but just type over the sine and put in a cosine of 2 theta. Okay, you don't need to write this on your notes or anything. So if you do 4 cosine of 2 theta, Okay, it's going to have 4 leaves. It doubles that. On a cosine, the number of leaves doubles that. You don't need to know that. It's just a little information I'm throwing in there. So if I change this to 4 theta, then you should see 8 leaves because it's a cosine. So it works like that. Okay, that's kind of cool, isn't it? Today in calculus, what we were doing was we were finding the area of that entire shape, okay, by using calculus and polar coordinates and doing integrals, okay? So you can kind of get into some pretty interesting shapes. Okay, so let's see. On this next thing here, let's put this one in. This one we're going to have to adjust our window on, just to show you how this one goes. So put in, you put in E, and then you want to put in theta over 5. If you have a older calculator, if anybody has like an 83, you have an 83 plus, I think you said, you may have to put it in like E raised to the theta over 5 in parentheses. The older calculators don't do that superscript, so you got to put it in like that. Okay, now I'm going to have you change the window on this one. So we're going to make, actually, theta can go as big as you want it to. So you won't get a full appreciation for this curve unless you make theta max big. Let's make theta max 100 radians. So let's just kind of start at 0, and then let's go like that. Now you can do theta step as 0.1 still. Now for the minimum, we're going to be pretty big. Let's do negative 50 to 50, and do the same thing with the y value on that, and then you can see what you're going to get. I'm going to scale that by 10, and then do the same thing on the y's. Negative 50 to 50 by a scale of 10. And then type it in, see what you're getting. What are you getting?
Spiral.
Yeah, spiral. Okay, yeah. Okay, that's why we had to kind of raise that window out, take that window out further. It spirals out like that forever, and of course that'll go get forever and ever. You can take your window like that. So it spirals in on itself like that. That's called a spiral. And with that one, you don't have to really do anything on that. I mean, you can just kind of wing it. I don't care. Okay, on that one, you're not going to graph anything like that. The purpose is to learn how to use your calculator and get kind of an understanding of how these curves go. The ones that turn out to probably be the most important are certainly the cardioid is something you would see in electrical engineering quite a bit. So those are the main ones that you want to be able to look at. So that'll just give you an idea. All right, the second part of this handout is really just information for you. Again, on the forms for this class, I'll kind of tell you what forms I want you to know. I want you to know certain forms, and the other ones are more for reference. So I want to go over the ones that you need to know, and you just need to write, make some notes to yourself on this, okay? So first of all, you want to know the equations of the circle. Did you need a handout? Because I've got some old handouts in that other pile. You okay? Yeah. Okay. All right, so you want to make sure that you know this, okay? These things right here, you want to know those. So if you have R is equal to A sine theta, that just means it's a center along the axis, okay? So this one would go like this. If you have A sine theta, what you would end up having, let me just show you kind of how this goes. If you had 4 sine theta, what this means is, since it's a sine, it means you're going to be on the y-axis. All right, so it means like when you go up 4, that's going to be a circle. The circle is going to go like this. Okay, you're going to go from 0 to 4, and the center of that circle is going to be halfway in the middle. So that's what the graph of 4 sine theta looks like. Okay, I'd like you to know that. You can actually figure that out without knowing that by changing it to rectangular coordinates. The other one I'd like you to know is, like, let's say you have R equals 4 cosine theta. It's the same idea. What you would have is you would go out on the positive x-axis because that's positive 4. Then you would start at the origin. The center would be halfway in the middle, and it would go like that. Now, that's a fairly easy structure to remember because the sine is associated with the y-axis on a unit circle, and the cosine is associated with the x-axis, okay? So you want to know those structures right there, okay? The other one that you want to make sure that you know how to do is This one's super easy, but if you forget it, you can figure it out. I want to just review that. So if you had something like r equals 2, that's a circle that has a center of 0, 0, and a radius of 2 like that. If you forget that, I'll go over what I taught you last time. If you square both sides of this equation, you get r squared equals 4, but what's r squared? What's that substitution? X squared plus y squared equals 4. Now, do you know that from earlier in the semester? I hope so. That's a circle, right, with a center of 0, 0, and a radius of 2. Okay, so again, if you don't remember this, you can figure it out by converting it back to rectangular coordinates. Okay, so I also want you to know the cardioids. Okay, most of these things on this handout you're not going to have to know for testing purposes, but I do like students to be able to spot a cardioid and a limacon and just know the difference between the two. I don't particularly like the way that this handout does this. It might be better if you wrote it this way. If you have r is equal to a plus or minus a cosine theta, or if you have r equals a plus or minus, a plus or minus sine theta like that, okay? Now I want you to just know that's a cardioid, and how that looks is like this. The key thing is an example would be 2 plus 2 cosine theta. If those two numbers are the same, it's a cardioid. Or if you had over here r equals 3 minus 3 sine theta. Okay, if those numbers are the same, it's a cardioid. It will have kind of a dimple. Don't worry about how it goes, but you can predict how this would go. If it's a cosine, it dimples around the x-axis. If it's a sine, the dimple goes around the y-axis. Does that make sense? I mean, that's just kind of what you're accustomed to thinking about with the unit circle. So I just want you to know the structure of that. Okay, rose curves, you don't have to know. You can write that down if you want to. Okay, I'm not going to, like on a test, say, is this a rose curve? I might say, is this a cardioid? Okay, that's important. I want you to know that because that's the one that shows up the most often. So you don't really have to worry about the rose curves. If I have you graph, you're going to graph on your calculator with a rose curve. Okay, and I went through about the petals. You don't have to worry about that. I do want you to know the limacon structure. Not graph it, you'll be graphing it with a calculator. So some examples would be r equals 2 plus 4 cosine theta, or something like r equals, for instance, 3 minus 1 sine theta. What makes that different than a cardioid is what? Those numbers are different. So if these numbers are the same, if that's a 3 and 3 and a 2 and 2, then it's a cardioid, but if they're different, they're a limacon. Now, I don't care about limacon with inner loop. You don't have to worry about that. I just want you to know it's a limacon, okay? Sometimes they have an inner loop. You don't have to worry about that, okay? All right? And sometimes they're dimpled limacons. I don't care about that, okay? You don't have to know that. Again, I want you to know what the difference between a limacon and a cardioid is. Everybody with me there? Okay, so you want to make sure you know that. That's what you're going to encounter the most often. Okay, lemniscates, you don't have to know that. We did a couple of lemniscates today, so you don't have to know those equations. And let's see, that's it. Okay, so the main things you want to know are the circles, the structure of the cardioid, and the structure of the limacon. Okay, is everybody good with that? Okay, so for example, on a test, if I say this, what is that? Cardioid, right. What if I do this? What if I say r equals 4 minus 2 sine theta? Then what is it? It's a limacon. That's what I want you to know. You don't have to worry about the dimpling and the convex and all that kind of stuff. I just want you to know the difference between the two, okay? All right, so that'll wrap that up, and then we'll start vectors tonight. That's where it all comes.